Okay, this lecture is called Drop the Base. It says keep calm and drop the base. It says anger is an acid that can do more harm to the vessel in which it is stored than to anything on which it is poured. That's a famous quote by Mark Twain. Now, I'm going to tell you up front that this lecture that we're going to be talking about, this idea of acids and bases, is going to be a difficult one. You're going to have to pay very close attention to the notes. You're going to have to write down lots of questions to ask in class, and you're going to have to spend lots of time practicing it because acids and bases can be somewhat difficult. Okay, so the first thing that we want you to be able to do is we want to be able to, for you to name acids and bases. Bases aren't a problem, we've already covered that, but acids is just a little bit different. We want you to be able to determine the concentration of hydronium ions. Another way of saying hydroniums is saying H plus, or more often it's H3O plus. It's the same thing. We want you to be able to calculate the pH and pOH of solution. You may have heard of pH, just whenever you're talking about a pool or something, but you probably haven't heard of the term pOH. We wanted you to be able to use stoichiometry to calculate the equivalence point of a titration. So you guys have already done a titration. We want you to be able to use stoichiometry to predict that point of titration. Okay? And then finally, we want you to be able to calculate a Ka, write out a Ka, Kb, and Kw expression. We'll get to what those are in a little bit. But first, what we already know. We know that acids are solutions with hydronium ions. So in other words, when I take an acid and I add it to water, what's produced is we get H3O plus. Now that's just one definition of an acid. You should know all of the definitions of the acid from previous things, so you should know the difference between an Arrhenius, a Bronsted-Lowry, and a Lewis base, or Lewis acids and bases. You should also know that bases are solutions in which hydroxide ions are formed. So when you take a base and you add it into water, you end up getting some sort of hydroxide solution. Okay? Acids and bases can be defined as strong or weak. A strong acid is one that disassociates completely. Um, so, in other words, if you take sodium hydroxide and you add it to water, all of the hydroxide ions come off. So you have nothing but hydroxide left. Okay, and you'd also have Na as well. But there is no more sodium hydroxide. It doesn't exist anymore because it's a strong acid or strong base, and because of that, it disassociates completely. So there is no more NaOH. It's just NAs and OHs. Okay, you can also have acids or bases that are called weak if they don't do this. So an example of that would be something like acetic acid. So you have CH3, COOH. What happens is it becomes CH3COO and it becomes H3O plus. Okay, but not all of it. Some of the acetic acid still remains. So because of that, we classify that as a weak acid or weak base. So you define it as strong if it disassociates completely. You define it as weak if it does not disassociate completely. Okay. Now, what we learned in the lab, we also said that indicators can be used to determine when the pH changes. So you have a solution that's red, and as you add in solution, it can change to yellow or blue or green or whatever you want, depending on the specific indicator that you're using. We also learned that acids and bases is considered to be a neutralization reaction. Remember, that's one of the three main ones that we said that we'll talk about whenever you get to a further chemistry course. We said there was redox. Okay, we said there was precipitate, and then we also said there was neutralization. And this is a neutralization reaction. You're neutralizing an acid with a base or neutralizing a base with an acid. We also said that titrations are a really, really important tool that chemists have in trying to determine specifically what the molarity of an unknown acid is or what an unknown sample is. So titrations are really key to when we're talking about acids and bases. Okay, the next thing we need to do is we need to work on naming acids, and you see this. All right, so naming acids is very similar to polyatomic ions with one big change, and that's the ending of what you have. So, for example, if you have something that looks like this, let's say it's HClO4. This ClO4 is perchlorate. Okay, so that's the polyatomic anion that we have there. It's perchlorate. If you look at perchlorate, perchlorate ends with an 8, which means that when I want to put it into an acid name, I have to replace the 8 with an ick. So what happens is when we rename this thing, it'll be named perchloric acid. Okay? You can do this with any of them. So for another example, this would be if you had something that looks like, okay, this right here is sulfite. And if you have sulfite, if you notice it ends, in this case, it ends with ite. So we have to replace ite with us. So this becomes actually sulfurous acid. Okay, and then whenever you have just an element by itself, like something like this, let's say H2S. Okay, remember, anytime you have an element by itself, that's just an ide. So this case would be, it'd be sulfide, would be the polyatomic ion. In order to put it as an acid name, though, what we would do is we would take this and we would put it in here. And so this would actually become hydrosulfuric acid. Okay, naming acid takes a little bit of practice, but if you can remember the ick gives 8, us gives ite, hydroic ide, it's probably the easiest thing for you to remember. Okay, naming bases is a lot easier because we've already done it. Okay, bases follow the same rules that we had for polyatomic ions. You name the cation followed by the anion, which the anion is always going to be hydroxide in this case, for the most part. Okay, if the cation is a transition metal, you indicate it with the oxidation number. So for example, if I wanted to do this, I would have to name it as copper 2 hydroxide. Because copper has to be an oxidation number of +2, oxidation number of hydroxide is -1 in order for them to balance out because of this subscript right here. Okay, you should be able to see what this is. Go ahead and see if you can talk to your teacher and figure out what that is. Okay, the next one says, how do we measure the strength of an acid? We know there are strong acids. We know there are weak acids based on how well they dissociate. A strong acid dissociates completely, where a weak acid doesn't. So the question is how do we measure that? And the most common way that we do it is actually litmus paper. You can actually take a piece of paper and you can dip it into a solution, and based on what color it changes, you have different pHs. A pH is a measurement of the strength of an acid. Okay. Now, pH paper is really good, but sometimes it's hard to distinguish between 3 and 4, or between 5 and 6. So another way that you can do it is you can actually use something called a pH probe. And all these are examples of pH probes. They look like styluses or things that you sign a credit card slip with at your grocery store. But they are ways of measuring how much acid there is or how much hydronium ions there are in a solution. So next, we get to the idea of pH itself. This is how we measure the acid strength. We use the pH scale. Now, if you look, the pH is what we call a logarithmic scale. You have a log there. A log is a button on your calculator, but it's a way of relating things that are very, very different to each other. Okay, so pH refers to how strong an acid is. The pH scale generally runs between 0 and 14, although you can have negative pHs and you could have, in theory, a pH above 14 as well, but that's generally the region from which you have them. Okay, that's what we're going to calculate. And in this side right here, you have the concentration of hydronium ions. Okay, the concentration is going to be measured in molarity. Okay, so we've experienced all this thing with molarity before. The pH is really the thing that's new in this particular case. Whenever you measure an acid strength this way, you can also measure the strength of a base in a very similar way. Instead of it being pH, though, with a base, we call it the POH. The only thing that's different is the fact that you have an OH because you're looking at the hydroxide ions instead of the hydronium ions. It's the exact same formula except POH is equal to the negative log of the OH, the hydroxide concentration. But everything else is the same. The pH scale, generally speaking, goes from 0 to 14. Okay. You have examples here of things that represent the different pHs. Battery acid has a pH of about 1. It's an extremely high pH. That's why they call it battery acid, and they tell you not to cut open a battery or things like that. Okay, lemon juice also has a pretty high acidity. It's what gives you that kind of pucker taste whenever you have lemonade or if you just eat a lemon. On the other side of the scale, you tend to have things like cleaning products. You have soft soap, you have ammonia, which is used in a lot of household cleaners, and then beyond that, you have a substance called lye, which is um, almost as corrosive as some of the battery acids that you see. So you see there's quite a big scale going back and forth between these, but generally speaking, we say things that have a pH that are under 7 are said to be acidic, and things that have a pH over 7 are said to be basic. And you can flip that for pOH. Now, how do we relate pH to pOH? And this is a formula that you have here. It's pH plus pOH has to equal 14. Okay. Now, this number actually came from the dissociation of water itself. Water will by itself turn into H plus and OH minus. It doesn't do it very much and it doesn't do it very often, but this 14 number is based on that. So if you find the pH, it's really easy to find the pOH. If you find the pOH, it's really easy to find the pH. So that's what you want to do. You want to be able to find one so you can solve for the other. In this example, it says that H2SO4 is a strong acid. What is the name, pH, and pOH of the solution of a 15.8 molar solution? Okay, so you have H2SO4, so you identify the anion. The anion is SO4, which makes it sulfate. Anytime that I see an 8, I have to replace it with an ic. So this becomes sulfuric acid. Okay, so that's the first part of the question. We've established the name. The next question that I want to do is I want to know what the pH of the solution is. Now, this H2SO4 was on one of your things, one of your lists of of strong acids to memorize. So H2SO4 is considered to be a strong acid. If it's a strong acid, that means it dissociates completely. All of it falls apart. Now, it's really important for you to recognize that whenever that happens, in this case, it just goes to H plus HSO4. The second H doesn't necessarily dissociate. So we're just looking at this first one right here. So if I have 15.8 molar solution, 15.8 molar solution, that means that after the reaction occurs, I have 15.8 molar hydrogen because all of this goes this way. So now that I've identified how much hydronium I have, I can use the formula pH equals the negative log of 15.8. At this point, you would need a calculator. There's no way for you to solve it without this unless you have a table of logs, which haven't been around for 30, 40 years. So because of that, when you plug these values in, you end up getting a pretty small number. Okay? And that's the whole point of this, is you can actually take really small values or really large values and you can relate them to each other on this logarithmic scale. And so when you do that, you actually get a value of about 1.2, negative 1.2 equals the pH. Okay, and that usually bothers people at some point because they say, well, didn't you say the pH scale is generally between 0 and 14? And we did say that. But we also said it could go below that. For strong acids, you could have a pH that is below 0 based on the concentration of the solution itself. So this is a possible answer. Now, once I have the pH as being negative 1.2, I should be able to solve for the pOH if I remember that pH plus pOH together have to equal 14. If I have a pH of negative 1.2 and I add pOH, that equals 14. That means my pOH is 15.2. So if you look, this question asks just about everything we've covered so far. It asks for the name, it asks for the pH, it asks for the pOH of a solution. So you should be able to figure that out. All right, the next example says write an equation for the ionization of water. What is the pH and what is the pOH of water? Okay, so the first thing we want to do is write an equation for the ionization of water. We did that earlier, but we'll do it again. So it says you have water, and I'm actually going to write it a little bit differently this time. Okay, it forms H3O plus OH. And a lot of people are saying, what's the difference between H3O plus and H plus? Really, there is no difference. Okay, they're the same thing, but different people like to write it different ways, so we'll just kind of interchange them. But if I write it this way, the way that I have written, you would need to balance this equation. So let's balance the equation. If you look, I would need two of these, and then I would make one of these and one of these. So I've written an ionization equation for water. Now the next question says, what is the pH and what is the pOH of water? Remember, by definition, water is considered to be neutral. So pH equals 7. So now I can calculate the pOH by saying that 14 equals the pH plus the pOH, or when you substitute 7 in there, you end up getting that the pOH is also 7. So water, pure water, this deionized water, or this pure water is said to have a pH of 7 and a pOH of 7. Now I will tell you that a lot of times when you measure water from the tap, it is not 7, and the reason for that is there's other stuff that's in water other than just pure water. There's minerals and so forth that can affect the pH. The example that we have here says you have a pH of 3.6. How many hydronium ions are present in the 25 ml sample of solution? So you have 3.6 is what you're looking at. The pH, remember, is equal to the negative log of the hydronium concentration. And in this case, I give you the fact that this is 3.6. So we have to do something with this log because I want to know what the hydronium ion concentration is, and this isn't working for me. I got to get rid of that log somehow. The first thing that I want to do is I want to move the negative to the other side. So I'm going to multiply both sides by -1, and when I do, I get this. Now, I need to get rid of the log. So whenever you're trying to get rid of something that's added, you subtract. Whenever you want to get rid of something that's multiplied, you divide, because those are considered to be the opposite functions. The opposite function of a log is raising something to the 10 to the whatever that is. So when I do this, 10 to the negative 3.6 and 10 to the log, the 10 and the log cancel out. And when they do that, you're left with just the hydronium concentration. And what that equals on the other side is that equals 10 to the negative 3.6, which in our case is about 2.51 times 10 to the negative fourth. Okay, that right there is the hydronium ion concentration. And a lot of times that's what a question is asking for. But in this case, all right, in this next one, once we've identified the fact that the molarity is 2.51 times 10 to the negative fourth, now what we need to do is we need to answer the question itself. It says how many hydronium ions are present in 25 mils of solution. So if we were to take this molarity, remember molarity is 2.51 times 10 to the minus fourth moles per liter. Okay, we need to change from liters to milliliters, or you could have converted 25 mils to liters. It doesn't matter. And once you do this, you can now multiply it by 25 milliliters. That right there would give you how many moles that you have. But remember, you're not asked for moles, you're asked for specifically how many of them are there. So the last step that you need to do is you need to be able to take this number for moles, and you need to be able to multiply it by 6.022 times 10 to the 23rd. Remember, that's the number of anything in a mole of anything. So when you do this and you work it all out, you should end up getting a number about 3.8 times 10 to the 18th hydronium ions, which is a lot. Okay, the next example says what is the pH of a solution containing 1.4 times 10 to the minus 10th molarity. And then it says classify the substance as an acid, a neutral, or a base. So what I'm going to do is I'm going to say, okay, the pH is going to be equal to the negative log of the hydronium concentration. And I'm going to plug in, I'm going to say negative log of 1.4 times 10 to the negative 10th. And when I finish with that, I can put it in my calculator. When I put it in my calculator, the pH is equal to positive 9.85. Don't forget about the negative there. You get a pH of positive 9.85, and when you get that, you have to classify it as an acid, a base, or a neutral. Remember, you have this big scale in which 7 is defined to be the neutral. Anything that is below 7 is considered to be an acid, and anything above 7 is considered to be a base. So we would take this substance and we would classify it as a base based on its pH. Okay, the next one says we are looking at the titration and equivalence point, and this is what we did when we were doing our titration. We had an indicator that told us where the equivalence point was, but now we want to look at it in a little bit more detail. Now we do realize that a titration is a neutralization reaction. What we're doing is we're taking and adding acid so that we can cancel out the base and turn it into water. And a common example of that is if you take hydrochloric acid and you mix it with sodium hydroxide. Basically what you have is a double replacement reaction. Okay, but this double replacement reaction is not a precipitate reaction. Instead, what it's doing is just neutralizing everything so that you produce water and salt. That's a common example of a titration where you're mixing an acid and a base. Now, sometimes it gets more difficult if you're using a weak acid and a strong base, and we will get into that a little bit, but that can complicate matters. The first thing that you do whenever you do a titration, though, is you need to choose an appropriate indicator. The indicator is when the color changes when a certain pH is reached. So, for example, you could have here, just as an example, this could be the pH is like 0 to 3, and this could be the pH at 4 to 7, and this could be the pH after it turns 8 plus. Okay, that could be an example of this particular indicator. But if you're looking for the pH, if you want to know how much it takes for the pH to reach 5, this indicator is not a great value because it's going to be at some point when it's in the orange. So you have to be careful when you choose the indicator. You have to choose the appropriate one with the right range for what you're looking for, and that takes practice. So a lot of times people like to use the pH probes instead because it gives you a more accurate view of what's going on. Okay, next we have the equivalence point. The equivalence point is the point at which you have a stoichiometric equivalent between acid and base. Okay, for example, if you were to mix a strong acid and a strong base together, the pH would be 7 because I've added just enough acid to get rid of all of the base, and so now I'm neutral. Okay, now that's where you've made them equivalent. That doesn't necessarily that the pH is going to be is going to be 7 for all of them. For example, if you were to mix a weak acid and a strong base, you would expect the pH to be greater than 7 because you have a strong base that has more of an impact than the weak acid. If you did the exact opposite and you mixed a strong acid with a weak base, you would expect the pH to be less than 7 at the equivalence point. We're going to stick with strong acids and strong bases for now, but we are going to revisit those, the idea of titrating a strong acid and a weak base. Okay, the next example says, speculate on the pH of the equivalence point for a solution shown below. Okay, so we've already kind of looked at this, right? You have this right here, which we're going to name. This is acetate, and then it's got the hydrogen, so we would call this acetic acid. Acetic acid is classified as a weak acid because it does not ionize completely. It does not dissociate completely. This is sodium hydroxide. It is classified as a strong base. So because of that, we would expect a weak acid and a strong base, we would expect the pH to be greater than 7 at the equivalence point. In this next one, it says how much 0.15 molar NaOH is needed it needs to be added to a solution of 25 mils of 15.8 hydrochloric acid to reach a pH of 7. Okay? So you're trying to reach a pH of 7. That's the neutral point where the amount of acid equals the amount of base. They cancel each other out. Now we have to look at it in terms of moles. You can't look at it and just say, oh, well, I'm going to add equal volumes or I'm going to add equal molarities. What you have to do is you have to look at it in terms of moles. So when I'm trying to find the equivalence point, this is what I do. I say, okay, I have 0.15 molar NaOH, and I want to know what the volume is. When I multiply molarity times volume, what I get is the number of moles. Now what you can do is you can say equals on the other side. And you can say, okay, this is what I'm titrating 15.8 molar, which is a very, very, very strong acid. And then you have a couple of choices right here. You can leave this thing as 25 mils, but what that means is that this answer is also going to be in mils. So notice whatever you put here is going to be over here. And that's okay. A lot of times we want it to be in liters, but you have to pay attention to the units. If you want it in liters, put it in liters. If you want it in milliliters, put it in milliliters. So you have this thing right here where you have an equivalence where you only have one variable that you're trying to solve for. So at this point, you would just take both sides and you divide them by 1.15. Whenever you do that, you get the volume of base needed is equal to 2,633 milliliters, which makes sense. You have a highly concentrated acid. Okay, this right here is 100 times more concentrated than the original sample. And we had 25 mils of it. So you would expect the equivalence point to be somewhere around 2,500 mils. And that doesn't even take into account the fact that it's more than 15 or more than 100 times. So you need to be able to find these stoichiometric equivalence points. And that's just the point in which the number of moles of acid equal the number of moles of base. Okay, so the next one says, what is the molarity of KOH if 73.2 mils of solution is added to 25 mils of 1.0 HBr to reach a pH of 7? Both of these things are classified as a strong base and a strong acid. So because of that, the stoichiometric equivalence point is where I will get a pH of 7. Okay, so here's what I'm going to do. I would say, okay, I have 1 molar HBr. That's my acid. I have 25 mils of that. You should know that because I'm putting it in mils, my answer or my other volume also has to be in mils, which it is. And then on the other side, for my base, I'm going to have 73.2 mils times some sort of concentration. That's the molarity of the base. When you divide both sides by 73.2, you're going to end up with the molarity of the base as 0.342 molar KOH. That right there is the concentration of the base based on the titration. So you titrate these things, you see how much is required, and then you can work backwards and you can calculate the molarity. Now, an important concept that you need to understand a little bit about is the idea of a buffer. And the buffer is the fact that you can have somebody consume a Coke, and a Coke is highly acidic. But whenever they drink it, it doesn't change the pH of their blood. And one of the reasons is the idea that we have a buffer system. And a buffer system is something that you can do chemically so that the pH does not change very much. And it involves taking a weak acid and a conjugate base so that whenever you add something, either an acid or a base, instead of changing it to hydroxide, okay, so if I were to add, if I were to add a base right here, instead of it going straight to hydroxide, this OH comes and takes this proton right here, and all of a sudden it's water, and you haven't changed the pH very much. Okay, all you've done is reduce the amount of weak acid. You haven't increased the amount of OH that's there. And it's the same thing here. If you were to add a strong acid right here, okay, that's got this thing right here, the pH should go way up. But instead, this H is able to react with this weak base, and whenever it reacts with the weak base, it turns it into water. It doesn't change it that much. Okay. So you should understand conceptually the idea of buffers. This is an extension in which we're going to revisit the idea of acid dissociation. So we said that acids and bases dissociate very similar to ions. In other words, we said with an ion, you could have something like NaCl, and it would dissociate into Na and Cl. You have the same basic thing that happens with an acid or a base. So you have the acid that separates into what makes it an acid, this idea of the hydronium ion, and its conjugate base, which is this. We can write a dissociation expression by taking what you have on one side and dividing it by what you have on the other. Specifically, it's called a Ka for acids. Okay, it's called a Kb for bases, and if you were to do it for something like this, it's generally called like a Ksp value. Okay, this isn't really what we're talking about at this point. So what you can do is you can write this Ka expression, and the way of writing it is you say the concentration of H, and that's what these brackets mean, times the concentration of A, and then you have on the bottom the concentration of HA that's left. So when we look at this for a strong acid, the strong acid disassociates completely, okay, or very close to it. It's not actually zero, but it's pretty close to zero. When you take a number and you take this and you make this basically zero, what does the Ka value do? It shoots way, 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 way up here. So the Ka value is basically meaningless for a strong acid. So instead, what it simplifies to is we kind of take that term out and we just say, okay, the initial concentration of strong acid equals the final concentration of hydronium ions. So if I have 1.4 molar HCl, when I put it in solution, I'm going to have 1.4 molar H plus. If I have 2.7 molar H2SO4, that's going to give me 2.7 molar H. You cannot assume that the second proton will come off. You can't do that. So this is an example of the strong acid. Strong acids are really easy to figure out. You just figure they dissociate completely. Where it gets a little bit trickier is when we look at the idea of a weak acid. When you do this, the weak acid partially disassociates. So these are going to be numbers, and this is going to be a number. So you can't say for certain that it's going to be initial concentration of strong acid equals final concentration of hydronium. You can't do this anymore. It doesn't work. Okay? Does not work. Okay, so because of that, you need to be able to figure out some sort of other mechanism for doing this. And it's best that you see this in an example. So if you're to look at the next example, it says the acid dissociation constant for acetic acid is 1.5 times 10 to the negative fifth. What is the pH of a solution of 0.15 molar acetic acid? How does this compare to the pH of 0.15 molar hydrochloric acid? Okay, so the first thing that you need to realize is that you need to write an expression in which you have the dissociation. So we have a Ka value. Ka equals, and we have to have the products on the top, and we have to have what we had to start on the bottom. I'm just going to call acetic acid HA. Okay, I know it's CH3COOH, but I'm just going to write it as HA just so I can see what it is. On the other side, it's going to become H and A. So my products that are going to be on the top are going to be my hydronium concentration and my acetic acid concentration. And on the bottom, I'm going to have my acetic acid that's remaining. So you're going to have this right here. This is the expression we're looking at. You are given the value of the Ka. That actually goes right here. And you are given the initial amount of acetic acid. Now, if that's the initial amount of acetic acid, some of that acetic acid is going to go away. When some of that acetic acid goes away, what I can say is that I'm going to have 0.15 minus X is going to be my value of acetic acid that I have left. So on the bottom here, I'm going to have 0.15, which is my initial concentration, minus X. Now, X is what fell apart. Now, the next thing we need to look at is how much H is produced. If I have one acetic acid that falls apart, it will produce one proton. So if X changes, that means I'm going to have X form. And it also means that when I do this, I'm going to form another A. So I have a new expression. I have the Ka value is equal to x squared divided by 0.15 minus x. So you get this idea right here. X squared divided by 0.15 minus x. Now, there's a trick to these that make it a little bit simpler. If you were to look at it, it looks like when you do this, this is going to be very, very tricky and hard to solve. You're going to have to use a quadratic and all that kind of stuff. You could solve this with a quadratic and you could get a more accurate answer. But you can simplify this by saying that when you multiply this number right here by x, it is going to be a very, very small number and have very little impact on the question itself. So you can actually take this x term and say that this is insignificant. It's a way of rounding, it's a way of simplifying, but it does work. So now you just have 0.15 times 0.15 or 1.58 times 10 to the minus fifth equals x squared. You can easily solve for x then, and x ends up being, remember x is the hydronium concentration, is equal to 1.4 times 10 to the negative third. Okay. Once you've established that that's the value of the hydronium concentration, now you can solve for the pH. The pH in this case would be the negative log of that. The pH that you calculate for it would be about 2.81. If you were to compare that to the pH of hydrochloric acid would just be, remember it completely disassociates, so it would just be the negative log of 0.15. And when you do that in the calculator, you end up getting a value of about 0.82. 0.82. So the pH is much, much lower for a strong acid than it is for a weak acid. And acetic acid is considered to be, it's not a terribly weak acid. So there is a big difference in the pH between the two, even at the same concentration. Like I said, this is tough. You're going to have to spend some time going over this and make sure that you understand it. Next, let's look at it for a base. A base works almost exactly the same way, except instead of saying HA, we say BOH. Then it goes to B and then OH. And we, instead of writing it as a Ka, we write it as a Kb. Now a strong base is basically the same thing. The strong base disassociates completely. Because it disassociates completely, this term is meaningless because it goes to infinity. So therefore, we can simplify that a strong base says that the concentration of the strong base equals the final concentration of OH. So if you have 12.3 molar NaOH, that means that you have 12.3 molar OH because it disassociates completely. Weak bases is very similar to weak acids. Okay, you have this expression. Because the weak base partially disassociates, you can no longer say that this is the case, and this right here cancels out. Okay, you have to go by this expression now. You can no longer say that the initial equals the final, because it's just not true. An example of this example E1, it says the dissociation constant of pyridine is 1.8 times 10 to the negative 9. That represents the Kb value. So what we have for pyridine, and I'm not going to write out pyridine structure because it's kind of long, so we're just going to say that that's the B for the base, and the B for the base is a BOH, and it's going to dissociate into a B and then an OH. Very similar to how the acid did it, with a base and a hydroxide instead of a acid or a hydronium and an A. So when you're writing the dissociation constant for this, it's going to be Kb is equal to B over OH divided by BOH. That right there represents the equilibrium constant value. So this right here equals 1.8 times 10 to the negative ninth. So you have 1.8 times 10 to the negative ninth equals, just like we had before, we don't know how much B is produced, so I'm going to write it as X. But for every B that I produce, I'm going to produce an OH as well, so that's going to be another X, divided by how much I had to start with, which is going to be 0.15, minus, and if you were to look here, for every BOH that falls apart, I'm going to produce one of those. So this is an X value as well. So when I lose one BOH, I make a B and I make an OH. Now, because this value is really small again, when you multiply this times X, it's going to be very small. You can cancel this term out. So this term is gone, and it simplifies your equation quite a bit. So now you would do 1.8 times 10 to the negative ninth times 0.15 and take the square root just like we did before. And when you do that, you're going to get a value of about 1.64 times 10 to the minus third. But remember, this represents the OH concentration because we're looking at OH there. So now that I have the OH, I can do the POH. POH is equal to the negative log of this, and the POH is equal to 4.78, and then we can go ahead and solve for there. We can do pH plus POH is equal to 14, which means that the pH must be 9.22. Okay, like I said, this is once again a really tough example of something that you should be able to do, but take some time, spend it with it, ask questions in class, and we'll move on from there. We'll get it. The last thing that we need to talk about is the dissociation of water. Now, we said that water dissociates, and it does. It changes to H plus and OH, and this is where you get the idea of the 14 from the pH and the POH. The rate of dissociation of water into hydroxide and hydronium is actually 1 times 10 to the negative 14th. They've actually measured it to be that. So since they have that, when you take the negative log of this number, you actually get this value right here, this 14. Sometimes they call this the pKw value because it's the dissociation of water value. We tend to not call that. Just say pH equals plus POH equals 14. But that's where this comes from. It comes from the idea that the dissociation of water is 14.